I A M J dagger is equal to the identity times delta I J times delta N M. And so this is my encoding of the quantum algebra that I'm now dealing with. And I want you to look at the following. If I take the components of Qij, I've got a product of an x with an x. And if I come over here, and I'm not going to write out all the indices here, I'm just going to do the product of an x with an x. I'm going to get something proportional to a dagger with a dagger. Just do the quadratic expansion. Something proportional to a dagger with a with a dagger, and a with a. Now if you look at what we've got on the board, you say, a dagger with a, I recognize that. That shows up as a piece of the Hamiltonian. And I'll leave you to put in all of the subscripts here. And you know a dagger is related to a dagger a just through this relationship. And so that also is tied to the Hamiltonian plus a constant. And you say, fine, that actually puts me, this operator actually, if you will, has a toehold, a footprint in the Hamiltonian for the shell model of Hamiltonian. But there are these a daggers, a dagger, and these a's, a. What is really going on here if I introduce these kinds of operators which are physically motivated to describe quadrupole degrees of freedom in the nucleus? And I'm now going to cut a lot of corners just to show you what is coming out of this. Because what is coming out of this is these quadratic products of x, they're going to give pieces proportional to the Hamiltonian. The oscillator Hamiltonian, it delivers energy shells. And so the shell model Hamiltonian, it partitions all of the quantum mechanical states in our system into energy shells. And I'm going to group them in the following way, so that here's each successive energy shell, but you look at the a dagger, that's a double creation operator. It will raise you not by one quantum, the oscillator, but by two. And so your a dagger will take you there, and your a will take you there. And if you come to what we know about nuclear structure, one of the first things you encounter in nuclear structure is something called the giant dipole resonance. And the giant dipole resonance is where you are exciting one nucleon across an energy shell, but then taking linear combinations of that so that you've got many, many configurations. And you end up with an excitation which is, we often call it a multi-particle, it's a superposition of one particle, one hole excitations, but many, many one particle, one hole excitations. And the giant dipole resonance shows up typically at about 12 MeV in an average heavy nucleus. And it's an enormously strong response of the nucleus. Now, there are details. It involves the fact that there's protons and neutrons, and this is because the actual response is electromagnetic. and so you've got to have charged particles to couple to the excitation medium. But these are the double raising and lowering. And there are two giant modes of excitation, which are 2h bar omega. I'm going to call these plus 2h bar omega, double raising, so I'm going to be adding 2 of these quantity or subtracting. And it turns out the double, these are the giant monopole and the giant quadrupole. Giant monopole resonance and giant quadrupole resonance. They both occur at roughly the same energy in an average heavy nucleus at about 17 MeV. In our algebra, we have now discovered that we have these giant resonance modes. And these are the modes that carry all of the strong collectivity in nuclei. I mean, we're used to looking at E2 transition probabilities at low energy in nuclei. We talk of a few hundred Weisskopf units. This has thousands of Weisskopf units if you use that measurement. So we have a spectacular bonus in defining this. We did it to describe quadrupole degrees of freedom, but it automatically couples in the giant monopole and quadrupole resonance modes. So let me stop there, and we'll have questions and discussion where I will encourage you to work with neighbors. But first, questions off the top about what we're looking at.